If a air parcel or air expands and cools, or the air compresses and warms, and there is no interchange of heat with the surrounding of the air parcel, this situation we will call it adiabatic process. Again, if a parcel of air expands and cools and compress, and because of the compression it warms, and there is no interchange of heat with its surroundings, this situation called an adiabatic process. As long as the air in the parcel is unsaturated. Unsaturated means the relative humidity is less than 100%. The rate of this adiabatic cooling or warming will always remain constant. This rate of heating or cooling is 10 degrees centigrade for every 1000 meter of the change in elevation, or in other words 5.5 degree Fahrenheit for per 1000 feet. So this rate applies only unsaturated air. That means air is not saturated. The more water vapor that air can hold to reach out the dew point temperature. So this rate only applies when unsaturated air, and it is called dry adiabatic rates or dry adiabatic lapse rate. As the air rising air cools, its relative humidity increase as the air temperature approaches to its dew point temperature. Dew point temperature means the temperature air is start to condense. If the rising air cools to its dew point temperature, the relative humidity cools to its dew point temperature. The relative humidity becomes 100%. If we do further lifting, and this further lifting result in condensation, and this will lead cloud forms, and a lot of latent heat will be released inside the rising air parcel. Because the heat added during the condensation, it offsets some of the cooling due to the expansion, and the air is no longer cools at the dry adiabatic rate, but it's a little bit less rate, and this situation is called moist adiabatic rate. In the moist adiabatic rate, we will say that the compression and the warm moist adiabatic lapse rate, because evaporation of the liquid droplet would offset the rate of compressional warming. So the rate at which rising and sinking saturated air change temperature, the moist adiabatic lapse rate, is little less than the dry adiabatic lapse rate. We know that dry adiabatic lapse rate is constant, but moist adiabatic lapse rate is not constant, but it's greatly varied with the temperature, with moisture content, because warm saturated air produces more liquid water than the cold saturated air. So the added condensation is warm saturated air liberates some more latent heat. So this results the moist adiabatic rate is much less than the dry adiabatic lapse rate. So we are, in a nutshell, we can say that in dry adiabatic process, if we go up, temperature decrease because our pressure decrease, so air molecule expand. This expansion lead air temperature to drop, and this drop of air temperature in dry situation is 10 degrees centigrade per 1000 meter. When we are entering into the wet adiabatic situation, that means the air is saturated. The air temperature is same as the dew point temperature. The relative humidity here is 100%. In this situation, our um, lapsing rate 5 degrees centigrade per 1000 meter. But this one is the leeward of the mountain. In the leeward of the mountain, when air is descending down, that means air is moving to downward. Air pressure is increasing. And this increased pressure means air colliding with each other more rapidly than previously. This rapid collision, when it's coming down, it's making heat, and that heat is making our air temperature to increase. So leeward of the mountain always is dry adiabatic lapse rate. That's mean we follow 10 degrees centigrade per 1000 meter. So this is the adiabatic rates. We have two adiabatic rates, dry and wet.